Hey, Joe here with another disc golf physics video. I actually just got done teaching for the day back in my office, but my last video got a great response and I got kind of excited to put another one out. But it has been a long day, so I'm going to put out a quick one. I want to talk about relative velocities and wind speed. It's going to be a fairly short video, but I think it's really practical and applicable to your actual game. So hopefully you find it interesting and hopefully it helps you a little bit. So in order to understand why a disc does what it does when you throw into a headwind or with a tailwind or with a crosswind, there's a few ideas that you have to understand. One, Newton's third law. It's pretty important. Newton's third law says that for every action force, there's an equal and opposite reaction force. So if I push on my desk, the desk actually pushes me back. So I can push on the desk, and it actually makes me go backwards because the desk pushes me and causes me to accelerate in the other direction. In my disc, if I'm throwing my disc nose up, it's bumping into air molecules, but those air molecules are bumping into it as well. It pushes the air molecules down, but all of those air molecules that it bumps into push it up, which causes a nose up disc to go up. And that's why they tend to go up in the air and stall out. Another concept we have to understand is relative velocities. This is what I meant when I was talking about wind speed versus ground speed. So if I'm on an airplane and I'm sitting next to somebody and I'm flipping a coin, according to me, according to the person next to me, that coin is just going up, coming back down. But if somebody's on the ground and has really good eyes and can see through the window and can see my coin flipping, it doesn't look like it's just going up and down because the airplane's moving. And as it's going, that coin goes up and down and actually traces a parabolic path according to somebody who's on the ground. So based on your frame of reference, those velocities look different and have different physical implications. So on the airplane, because it's not accelerating, just going at constant velocity, if I flip the coin, everything behaves like it normally would. It's called a non-inertial reference frame, I think, or an inertial reference frame. You can look that up if you want more information on it. As long as it's not accelerating, moving at a constant velocity, I can flip it up. It's going to just behave like it would if I was sitting still. But according to the person on the ground, they see it as a parabolic projectile motion trajectory. So that was a little bit in the woods, but if you followed me, great. If not, there's lots of videos on it. You can check it out. How does that apply to disc golf? Well, what makes the disc follow the path that it does? When I throw it, it leaves my hand at a high speed. It starts to slow down after I let it go because of the drag of the wind that it bumps into. Again, Newton's third law causes it to slow down as it's pushing through the air. But it's got a high speed stability and a low speed stability. I'm right hand backhand, I throw it, it's going to go a little right and then come back to the left. That has to do with its gyroscopic progression. It's content for another video. I wanted to make this one kind of quick. All right, so why does it go through that gyroscopic progression? Well, because of the air molecules that it's interacting with, just kind of like that Newton's third law thing. It gets a little complicated because of the lift going over the top arch of the disc. And I'm actually researching this a little bit to learn more myself. The faster it's moving through the air, the more it's going to feel those effects. It feels those effects because it's moving through the air, and the faster it's going, the more it's going to feel those effects. When I'm throwing on a calm day, the air is sitting still relative to the ground. So how fast it's going relative to the ground is the same as how fast it's going relative to the air. But if the air is moving, then suddenly you have a different story. It's kind of like with the airplane and the coin. The coin's motion is added onto that airplane motion. So now if I'm not flipping the coin, if I'm throwing the coin forward, according to me, it's moving forward, but according to the person who's watching outside, it's going really fast. It's going the airplane speed plus the speed that I threw it with. So that's kind of like what's going on with my disc in a headwind. I throw it into a headwind, and the disc is moving this way relative to the ground at a certain speed, and the wind is moving towards me at a certain speed relative to the disc. So those two velocities end up adding up. The vectors add up to give me a wind speed, an air speed that's faster than it would be if it was not windy. So the disc feels like, compared to the wind, it's actually moving faster. So its relative velocity, relative to the wind, is faster than it would be if the wind wasn't going. So into a headwind, it acts like it's going faster than it really is, so it's going to act more understable, like it does when it's moving at a high speed. If you throw in a tailwind, the exact opposite happens. So relative to the wind, relative to the ground, it's moving at the same speed it would be when I throw it, but the wind is moving with it. So It's like two cars going down the highway. A guy standing on the side of the road watches and sees them both go by at their speed. But if I'm passing one of the cars, it looks like that car that I'm passing is going backwards. It looks like it's going slower than it really is because I'm moving along with it. Those relative velocities subtract from each other in terms of the disc moving through the air. And it acts like it's more overstable because it feels like it's going slower relative to the wind. The wind is moving with it. Whew. That was a lot. I'm trying to kind of go fast, so I hope that made sense. The crosswinds, if you have a left to right or a right to left, that has more to do with that Newton's third law idea. If it's angled like this and there's a wind going this way, it's going to push it down. If it's angled like this and there's a wind coming this way, it's going to lift it up. Newton's third law says when the wind hits it, it's going to cause the wind to go down and the disc to go up, an equal and opposite amount of force. That was a lot of physics, and it looks like I did it in like 6 minutes. So I don't know. We'll see how you guys like that video. If it was good, let me know. If I didn't do a very good job of explaining it, I apologize. Feel free to leave a comment. Let me know that too. I hope that helps. It helps you conceptualize what's going on when you have different winds going in different directions. Otherwise, thanks for watching, guys. I got more of these planned as the semester progresses.